Hello friends, I am coming with question number 7 of Pathfinder Newton laws of motion. What is the wording of this question? Question is saying that a small metal ball is being pulled gradually on a fixed frictionless hemisphere as shown in the figure. Radii of the ball and that of the pulley are much smaller than that of the hemisphere. As the ball slides from the bottom to a position close to the top of the hemisphere, how do the magnitudes of the pulling force F and contact force R between the ball and the hemisphere changes? So let's say what is the question. I want to draw carefully. So this is a sphere. Here one sphere is placed on the ground. It is the fixed sphere like this. Okay, and one ball is placed, suppose this is a center, and from the center one ball is placed here, and from this ball a pulley is placed here, this pulley, and we apply a force F on this pulley in this direction. Okay, then what are the forces is acting? I tell you, first of all, normal is acting, and normal is given here contact force R. So here I am writing R. So it is the R and mg downward. And second force is this force is say called F. Is it clear? So my dear friend, if let us assume this angle is theta 1, this is a small r, this angle is theta 2, and this angle is theta 3. So we can say that for if I draw the carefully forces in vector form, then this is a point of the ball. One force is acting here, it is R. Other force is F, and downward force is mg. Okay, my dear friends, you can say that, sir, if this angle is theta 1, then angle between R and mg is pi minus theta 1. So this mg force, so we can say that this angle between R and theta 1 is pi minus theta 1. Simply, you can say that this angle is theta 1. So this angle is theta 1. So this angle is 180 minus theta 1. Understood? If this angle is theta 2 as given, so this angle is pi minus theta 2. So this angle between these two is pi minus theta 2. And this angle is theta 3. So the angle between F and mg is pi minus theta 3. So in case of the ball is equilibrium, so I apply the Lami's theorem. So Lami's theorem is saying that, my dear friends, it is R upon sine pi minus theta 3 is equal to mg upon sine pi minus theta 2 equal to F upon sine pi minus theta 1. So 180 minus theta is the sine theta. So R upon sine theta 3 is equal to mg upon sine theta 2 is equal to F upon sine theta 1. Now my dear friend, I draw the geometrical structure. So this is the pulley point to the center of the hemisphere to pulley center. So this radius is height is r plus small r plus h. H is the height from the ground, from this surface. So this is the height h. So this is the r. So total r plus h. This point you knows very well, it is small r, and this is the length of the string, which is L. So my dear friends, if this angle, I can tell you, this angle is theta 1, this angle is theta 2, and this angle is theta 3. So from geometry, applying sine rule. Okay. So if you apply the sine rule, then you can say that, sir, it is L upon sine theta 1 is equal to R plus H upon sine theta 2 is equal to R upon sine theta 3. My dear friend, this is the equation number 1 and this is the equation number 2. If we divide the equation 1 divided by equation 2, equation 1 divided by equation 2, then you can write, here you can say that the capital R by small r is equal to mg upon r plus h equal to f by L. My dear friends, I tell you clearly, the radius of hemisphere is always constant. Okay. So if the radius of hemisphere is constant, so question is asking f increases, r decreases, f increases, r increases, f decreases, r remains unchanged, f remains unchanged, r decreases. I tell you one thing, just listen carefully. If f decreases, then L is also decreases. F decreases, L is also decreases. Is it clear or not? And mg is constant, r plus h is also constant, so it is 100% set. So if f decreases, L is also decreases, but r is constant, so capital R is also constant. So means if you change the f, the reaction force does not changes. So what are the correct conclusion? F decreases but R remains unchanged. So the correct answer is this. Thank you so much for watching this video. Bye bye.